Now we are going to discuss the mass discharge through nozzle. So this is the derivation we are going to learn today, the mass discharge through the nozzle. So let me consider a nozzle a convergent nozzle which has inlet and exit. So what are the parameters involved in a nozzle for the steam to flow through it? The parameters which are involved for a nozzle for the steam to flow into it is the pressure of the steam at inlet, specific volume of the steam at inlet, and the area of the nozzle at inlet, and most important thing, it is the velocity of the steam at inlet. So these are the parameters which is very important for the nozzle to for the steam to flow into the nozzle. So pressure, specific volume, area, and velocity. Similarly, at the exit, the steam at which pressure it leaves the nozzle, it is written by P2, specific volume V2, area of the nozzle which influence it, and velocity of the nozzle, at what jet of steam which goes out of this nozzle. These are the parameters involved. Okay, now let us have some assumptions for this derivation of the mass discharge. The first and foremost important assumption is we consider that this nozzle is of convergent type of nozzle. So in convergent type of nozzle, what happens is the velocity at exit is greater, it's very greater than velocity at inlet. So in that case we are going to neglect the velocity at inlet, because compared to our exit velocity, inlet is very small. So this is the assumption we are going to make. So to start the derivation, we need to know the governing law or equation for the nozzle to flow, which means the steam which flows to the nozzle. The steam flow through the nozzle is governed according to the law of expansion. Law of expansion. So that law of expansion is nothing but PV to the power of n is equal to constant. So it is a polytropic law of expansion. Basically in nozzle, the fluid or the steam get expanded. The fluid or steam get expanded. Fine. So this is the governing equation. PV to the power of n is equal to constant, where n is nothing but polytropic index. So the value of n depends on the type of steam. So basically when the steam is wet, which means partially dry, so the value of n is given by equation 1.035 plus 0.1x. So this is the equation where x is equal to dryness fraction. So for dry steam, what is dry steam means? It is 100% steam, or dryness fraction will give you 1. So the equation will be equal to 1.135. For superheated steam, the value of n is 1.3. So all this value of n, it is experimented values, which is successfully working in the practical application of the steam nozzles. So these relations are basically an experimental value, and this equation is known as Zenner's equation. So n is equal to 1.035 plus 0.1x. This is given by Zenner. So that is why it is called as Zenner's equation. So let us move forward. So now let us find the work done per kg of steam. during the cycle. So basically we use Rankine cycle for the steam to expand in the nozzle. So the work done formula is given by n divided by n minus 1 v1 minus 2 v2. So this is the work done formula. We need to understand. So let me call this equation as 1 governing equation, second equation as 2. Okay, now let me continue this derivation. Gain in the kinetic energy of the steam is nothing but V2 by 2 minus V1 by 2. So this equation is nothing but kinetic energy equation of mv square. So we are considering mass as 1. So the equation will be v square by 2. That's what I have written here. So that is equal to v2 v2. So why I have written v2 by 2 means, as we know, we are going to neglect the inlet velocity. We are going to neglect the inlet velocity so that the remaining equation will be v1 square by 2. So the kinetic energy gained in the steam when it is flowing through the nozzle is v2 square. v2 square by 2. Fine. Now gain in the kinetic energy will be equal to enthalpy drop in the nozzle. So the formula will be v2 square by 2 will be equal to enthalpy drop is h1 minus h2. So when I write this particular equation and show you in terms of HS diagram, let me write the HS diagram. So this is the pressure lines P1, P2, so when it is an isentropic expansion, there will be a straight line. So this is process 1 to 2 dash, an isentropic expansion where S1 will be equal to S2, but practically due to friction there will be a small deviation let me write as 2. Let me write that as 2. So this is what we are going to find. There is a small entropy drop that has been happened in the process 1 to 2. So let me continue the derivation. So let me take this as equation number 3. Now, given kinetic energy that is equal to enthalpy drop that is equal to work done during the cycle. So this is nothing but V2 square by 2 that is equal to H1 minus H2, again that is equal to work done by the cycle. We have written that n divided by n minus 1 P1 V1 minus P2 V2. So all this are interrelated to each other. Let me write this as equation number 4. Fine. So let me consider only these two equations. So V2 square by 2 that is equal to n divided by n minus 1 P1 V1 minus P2 V2. So what I'm going to do is I'm going to take this quantity outside. So n divided by n minus 1 P1 V1 that will give me 1 minus P2 V2 divided by, because if I remove this outside I should divide this V1 V1. So let me consider this equation as 4a. So now let us use the polytropic equation, the governing equation, the main equation for your process. P1 V1 to the power of n equals to P2 V2 to the power of n. So PV to the power of n is equal to constant. So V1 by V2 by V1 will be equal to P1 by P2 to the power of 1 by n. We just taken specific volume on one side and pressures on the other side, and we assigned the polytropic index. Okay. So V2 equals V1 into P1 divided by P2 to the power of 1 by n. So let me call this particular equation as equation number 5. Equation number 5. Now, substituting for V2 in equation 4a, we get, so V square 2 by 2, that is equal to n divided by n minus 1 P1 V1 1 minus P2 by P1 open bracket P1 by P2 to the power of 1 by n. We just substituted the value of this in equation. Okay, let us move forward. Okay, I think this will be correct. Sorry. Now, let us further simplify this. P2 by 2 equals Pn divided by n minus 1 P1 V1 1 minus, when I simplify this, what happens means I'm going to get P2 P1 by P2 to the power of 1 minus 1 by n. So if I simplify this particular term, so when I do that, I'll get this particular equation. So further, if I simplify this, I'll get P2 by 2, that is equal to 2 into, let me take this 2 here, n divided by n minus 1 P1 V1 1 minus P1 P2 to the power of 1 minus 1 by n. So want to make one small modification here. 2 into n divided by n minus 1 P1 V1 1 minus P1 by P2 to the power of n minus 1 by n. I'm just taking the LCM of the powers and I'm going to make it a square root. So let us have a look at this equation. Let me call this equation number 6. Now we are going to introduce the mass flow. M dot equals area into velocity into density, rho AV, the mass flow rate. So the density can be written as 1 by specific volume. So our mass flow rate will be AV by small v. So we are interested in calculating the exit velocity of the nozzle. So considering mass flow rate at exit A2 V2 divided by specific volume at the exit. Let me consider this as equation number 7. Now moving forward, let me move forward, substituting the value for the mass flow in equation. So which equation? Number 6. So we get m dot is equal to A2 V2 in the case of velocity 2. Let me substitute this equation. Square root of 2n divided by n minus 1 P1 V1 1 minus P2 by P1 to the power n minus 1 by n. So we know V2 can be written as V1 to the P1 into P1 by P2 to the power of 1 by n. So m dot will be written as A divided by V1 into P1 by P2 to the power of 1 by n. That is into 2 into n divided by n minus 1 P1 V1 1 minus P2 by P1 to the power of n minus 1 by n. So let us move forward. So I am going to multiply this particular term to this equation, or I am going to substitute this term into this equation. So we'll see how the equation, we can transfer this to left side of the equation. So m dot equals A V1. So since we are taking this inside, let me consider only A to square root of 2 n divided by n minus 1 P1 V1 divided by P1 P2 to the power of, if I take inside the square root, it will be square of n P1 square 1 minus okay. So further continuing, A into square root of n divided by n minus 1. So I'm going to take this term inside. So before that, we'll see what best we can do in this derivation. I can remove this e square p, so v1 divided by v1 that can be written as v2 by v1. The power won't change, we are just interchanging this. 1 minus p2 by p1 to the power of n minus 1 by n. Further simplifying, n divided by n minus 1 p1 p1. I'm going to take this inside. So p2 by p1 to the power of 2 by n minus p2 by p1 to the power of 2 by n p2 by p1 to the power of n minus 1 by n. So A into after this, we'll see how the equation goes. So the equation will be like this. P2 by P1 2 by n minus let me substitute here 2 by n into n minus 1 by n. So common will be n. So it will be n minus 1 only. So P2 by P1 to the power of n minus 1 by n, it will become plus 1. So 2 of n written as so we got n plus 1, just reject it. Into so this is the mass. So now the mass flow rate depends on one particular quantity, that is P2 by P1 to the power of 2 by n minus P2 by P1 to the power of n plus 1 by n. So this is the quantity which is influencing the mass flow. So let me consider R equals to P2 by P1. Then the equation looks something like this: R to the power of 2 by n minus P R to the power of n plus 1 by n. So if I differentiate the above equation, so dm by with respect to dr, I'll get so 2 by n R to the power of 2 by n minus 1 minus of n plus 1 by n R to the power of n plus 1 by n minus 1. So if I substitute all those things, what happens to my equation is I'll get R, value of R will be get R in terms of 2 divided by n plus 1. So that is equal to P2 by P1. That is also equal to P2, it's a throat. That is also called as a critical pressure. What is critical pressure? In that the Mach number of the fluid flow will be equal to 1. So now applying the condition. Now applying the condition for dry steam, value of n is equal to 1.135. If I substitute in this value, the value of R I will get 2 divided by to the power of n divided by n minus 1. Forgot this one. So I will get 0.577 for dry steam. For superheated steam, n equals to 1.3. The value of R (0.545). Now finding maximum flow, that is nothing but m dot max, that will be equal to, when I substitute in this equation, when I substitute everything in this equation, I'll get 0.635596 E2 to the power of P1 V1 for dry steam. Zero point 6672682 P1 V1 for superheated steam. So this is the derivation.